Thank you, Laura. Yeah, it's really exciting, is the short answer. So yes, so I'm very excited to give this talk today for reasons that you'll see as we keep going. It was mapping that got me into studying exoplanets in the first place. But I also spend the rest of my science life figuring out how to get computers to work. Actually, that's really true. It's figuring out how to get computers down, over. Oh, like I tap it maybe? Okay, well, we'll keep working. So yeah, so the rest of my career is running three-dimensional models of atmospheric circulation of planets, predicting temperature structures, wind speeds. There's no talk about that at this workshop, so you'll just have to trust me and other people who have alluded to there being large spatial differences and how that works. So let's just say there are, especially on hot Jupiters, which are also the best targets to do atmospheric characterization, especially when we're trying to do really precise measurements. So we'll just take that as given and keep going. I also don't actually love this term transit spectroscopy because it sounds a lot like transmission spectroscopy, and that's only one part of the way that we characterize transiting exoplanet atmospheres. And in fact, in this talk, I'm going to be describing how we use not just transit, but Eclipse as well. I'm going to be skipping over other ways that we do get some spatial information about exoplanet atmospheres, but because I need to limit my time to just ways that we get 3 dimensions. So Laura gave a wonderful talk about phase curves and how that gives us 2 dimensions of information, because we get information in longitude around the planet. And when we measure spectra, that gives us depth into the planet, but we don't get a 3rd dimension. And I also want to point out, even though we're focusing in this talk on planets that transit, because we want to use these special times, of course, those phase curves also are just rotational curves. And so you can map that way as well for directly imaged planets or anything that rotates. I also want to remind you of the lovely talk we heard from Matteo about high resolution spectroscopy. And this is one of my other favorite methods of characterization. It gets you unique information, for example, the motion of the atmosphere itself. And there's some really nice work that people are starting to do, figuring out how we get things like phase curve information from high resolution spectroscopy. But in this talk, I want 3 dimensions. And so I'm going to talk about how we get that from the special times of transit and eclipse. And I'll describe how those particular times let us actually get information in all 3 dimensions of a planet's atmosphere. So, it was really fun actually putting together this talk because I got to think about the ways that eclipse mapping and transit mapping have shared commonalities. Of course, there are differences. The eclipse mapping, we're measuring the day-side structure of the planet. In transit, we're measuring the region around the terminator, the day-night divider. But in both techniques, we're getting 3D information from measuring the shape of light, of how light changes with time, the light curve, and doing this spectrally at different wavelengths. And with both techniques, we have to think carefully about how we actually pull that 3D information, which is in the data, out, because we have to make assumptions. So before I jump into these exoplanet maps, I'm going to use some more historical examples of using eclipse mapping in other astronomical techniques, because exoplanets didn't invent this technique. This is not even astronomy. This is just a cartoon. If you have a shape and you block the light from that shape, you lose your brightness over time. if you change the pattern of brightness across that shape, and then block it, that will alter the light curve, how you lose that light with time, or if you reveal it, how you regain the light with time. And that's the basic concept of eclipse mapping, is that you're measuring the brightness gradient in the direction that you are blocking, also transit mapping, I should say. So in astronomy, one of the early techniques of eclipse mapping was to use stars eclipsing each other to map. So now you have a star, you block it with another star, and in this case, the one that's being blocked is a white dwarf, the one in front is a main sequence star. And so you can see early in the 70s, this was done. These are the data. As the star from the white dwarf is lost as it goes into ingress, and then as the star from the white dwarf is revealed as it comes out from egress. And using these measurements, they could constrain the limb darkening of the white dwarf. This is the sun. It's not the white dwarf, but you know, limb darkening is a thing, and limb darkening is a thing that depends on wavelength. If you don't know what limb darkening is, I'm sorry, I'm going to skip it because it's not actually a perfect analogy for what's going on with eclipse, with planets, the way that we're doing it. So I don't want to linger too much, but just to say that the dimension that we're measuring, the spatial change in brightness, comes from the shape of that light curve. And as you may know, if you've tried to fit exoplanet transits, the limb darkening changes with wavelength, because light emerges from stars differently due to different opacities in the atmosphere. And so we get 3 dimensions from the shape of the light curve and the difference in that shape with wavelength. I'm now going to use this other example to get to my point about how we extract that information. So another application of eclipse mapping in astronomy are these compact or cataclysmic variable systems, where you have one star donating material to its compact star, white dwarf, and that flows through an accretion disk onto the star. And these can be eclipsing each other, and so you can use, again, the eclipsing star to map out the shape of the disk. And so I made a little animation by taking screenshots from panels of a paper. And so here you have the light curve itself on the left. You have a reconstructed image of the disk in the middle, and you'll see a shadow move across that, coincident with the animation or illustration on the right of the orientation of the star relative to the accretion disk. So as we step through the phase curve, we're stepping through the star blocking different regions of the disk, and that impacts how the shape of the light curve changes with time. In this example paper from the mid-80s, I was technically alive. I bet many of you were not. This study demonstrated how the assumptions made in reconstructing the map matter. So in the top right over here, you have a simulated accretion disk structure that was used to make the simulated light curve. And so the accretion disk is brighter at the center. Maybe there's a blob due to some physics happening. But if you then measure, if you pretend that you've measured this light curve and you want to try to back out what the disk actually looks like, now you only have one dimension, right? You just have amount of light versus time. And so even though there's 2-dimensional information in these data, you have to apply an assumption to back out that extra dimension. And you might choose different assumptions. You might choose one that's kind of model independent, that's requiring something about how the map varies in space. Or you might say, well, accretion disks should generally have some physical characteristic, like being axisymmetric. And so that's the assumption that will shape how we pull the information out of the light curve. And you get different answers. Now, they're not too far off from the original image, but it is important, I'm going to say this over and over, that the assumptions you use shape the answer you get. And you really need to take those into account when you're trying to compare to what you think the truth may be, because you may not be able to achieve the truth exactly based on your assumptions. Yes, that's what I said. Okay, so eclipse mapping we'll start with. It's slightly older in exoplanets than transit mapping. Also, transit mapping isn't even like a term people are using. I just decided it's the helpful term to use in this talk. We do use eclipse mapping. The idea here is that as the planet, same kind of as that white dwarf, as the planet goes into eclipse behind the star and comes back out, the stellar disk slicing off different regions of the planet disk lets us measure the gradient across the planet disk in one direction going into eclipse and the other direction coming out of eclipse. And so you have 2 dimensions and 2-dimensional information. Also, that photo of the Sagan Summer Workshop from 2009 was amazing. And one thing, just to like put history in it, in 2009, I had published my first paper in exoplanets saying that we would be able to do eclipse mapping with JWST. It was so exciting. Oh, no. Okay, no. Too much. I was also wrong, but I was delighted to be wrong because with the Spitzer Space Telescope, remarkably, 2 different independent teams took a data set for one of our famous hot Jupiters, HD 189733b. These are 8-micron data. And there's like half a dozen eclipses that were measured, as well as a partial phase curve. And all of that information actually was finally sufficient precision to make a very kind of rudimentary map of this hot Jupiter, where you get this eastward shift of the bright spot in agreement with previous interpretations of phase curves for this planet, or a phase curve for this planet, but actually exploiting that ingress and egress information as well. But 1 wavelength, so a 2D map, not 3D. And in one of those papers, the one by DeWitt and his collaborators, they really nicely sketched out how the map that best fits those data depends on the framework that you use for the mapping. So on the top example here, they said, well, spherical harmonics can be a perfect basis set for describing a pattern on a sphere. Give yourself a higher enough order to your spherical harmonics and you can make any map, right? And that's what you get if you use spherical harmonics. On the bottom here, they said, well, we have expectations about the spatial patterns there should be on hot Jupiters. And if we use a parameterization that should allow for those spatial structures, then you get the map on the bottom. And so there's some complication, which is the better choice. Well, we proposed an extension on this, a way to think about a model independent method that gives you the most information possible. So it's one choice. I think there are other good choices, but this one gives you the most information possible. And the idea here is that whereas spherical harmonics are great for mapping a sphere and they're orthogonal on the sphere, what we're actually measuring is light curves. Right? So you could take any of these spherical harmonics, put it on a sphere, integrate it through an eclipse, and you get a light curve associated with it. And these light curve components are not orthogonal. So if you're fitting your data with these spherical harmonic light curve components, you will get degeneracies between your different terms. And so it was an easy fix. You run these spherical harmonic light curves through a principal component analysis, which is just some matrix math that takes any data set and figures out orthogonal dimensions that best describe the spread in that data. Don't worry about it too much if you don't like the math, but if you do, it's really fun. And what you get out of this then are light curves that are orthogonalized, so they're not going to be degenerate in your fit, and they're ranked in terms of how much variation they could explain in your data. And so you know which ones have the potential to be maximally informative. So you can then fit with those, what we called eigencurves. And each eigencurve is a sum of spherical harmonic light curves, which means each eigencurve also corresponds to a map that is a sum of spherical harmonic maps. And so the math of it is really quite elegant and fun. And since we're all doing hands-on stuff, if you ever want to play around with Eclipse mapping, there is a code available on GitHub that uses this mapping technique. There's also a JWST data set that's used this mapping technique. So this is from the ERS, Early Release Science Transiting Exoplanet team. These are some instrument observing WASP 18b, which is a famous ultra-hot Jupiter, a very bright system. I'm a theorist, I'm sorry. And this is the broadband secondary eclipse observation. And so these data are precise enough to actually map the planet. The mapping that was done is the responsible way of doing it, where you fit your systematics at the same time as your mapping signal, and you fit you try a bunch of different mapping components, see how many are statistically allowed by your data. But I'm gonna kind of walk you through the components sequentially so you can get a sense of how they come together. So here, again, in blue are the same data. And now you're seeing a fit of a uniform component map. In the middle, you're zooming in on those regions of ingress and egress. And on the right, you see the map that corresponds to this curve. And it's just uniform, right? No spatial information. And it does not fully explain the data. So you add another term that allows a gradient across the day side. You add another term that gives you an east-west shift. You give another term and another term. And I'm not going to show you the map itself because there's some weird nuances and I couldn't figure out how to make it too simple. So instead, I'm showing you this beautiful animation made very nearby here because based on the gradient that was measured across this planet's day side, we see interesting indications of what might be some really cool physics going on the planet. But I'm not going to tell you because I don't have time. But that was one dimension, right? We summed all the light over the instrument and we're just getting a one-dimensional brightness map. But I said, I want to talk about three-dimensional mapping. And so now we come back to this image that I gave Hannah a hard time about before she showed it in her talk, which is why she referenced me. Because we know, as many people have said in many different talks, that different wavelengths probe different depths into the atmosphere. And on the Earth, this is reflected light, so not a great analogy to what we're measuring in thermal emission. But if we switch to a wavelength where we are measuring thermal emission from the atmosphere, then you can see that whether we're observing the light where there's not a lot of opacity or where there is a lot of opacity, you're getting emission from physically different layers of the atmosphere. And so if we take our beautiful JWST data for this system that does have spectral information, then we can make maps that probe different depths into the atmosphere. In the interest of time, I'm not going to go through the real nitty-gritty of how to do this. And in fact, these techniques are still actively being developed and refined and tested. But the basic idea that we have so far about how to do this 3D eclipse mapping is basically that you start the same way as before. You use your light curve to make a map, but you do it separately for each different wavelength. And then you have a set of maps. And we have a couple different options, a couple different techniques that we're trying out. One is that you take those maps of brightness at different wavelengths and you stack them together into a data cube, and then you use a clustering algorithm to identify spatial regions in latitude and longitude that have similar spectra. And so then you can make the spectral spatial groups, and it's a fairly model independent way to try to figure out what's going on in the atmosphere. And then if you want to retrieve on those different groups, cool. Another approach, which is less model independent and a bit more of a parameterization towards real 3D structure, is to take these brightness maps at different wavelengths, convert them to brightness temperature, and then figure out how to layer them, shift them up and down in the atmosphere until when you run radiative transfer through that atmosphere, you get spectral light curves that match the ones that you've observed. So stay tuned. I can't show you any results yet because these talks are being broadcast too much, but I mean, it's great, but I can't show you the results yet because there's a paper in prep to do this 3D mapping with WASP-18b. And I know there are JWST spectral maps being worked on of other targets as well. So really, we're about to see the results for this. And there's a lot of work being done to, now that we actually have data finally that are good enough for 3D mapping, to lean into the methods and think a little bit more carefully about how to do this best. Thank you, Laura. So in my last little bit of time, I'm going to flip to transit mapping. So here, again, we're going to get 3D structure, but differently. We're not seeing the emission from the planet. We're seeing the light filtering through the planet's atmosphere during transit. So we flip the planet around. We look at the night side, and we're not seeing emission, but we may expect spatial differences anyway, because if one side of the planet is hotter, then it should be puffier, right? We saw the scale height introduced by Hannah. We saw it again from one of the talks this morning, Leslie maybe. And so if you have a hotter side of the planet, its scale height will be larger. And so it's physically going to be blocking a larger region of the stellar disk. And here's an example. The black line is from an actual 3D model. The red and blue curves are if you don't have circulation in the atmosphere, and you see that you actually get more extended atmosphere on one side. And similar to eclipse mapping, the planet is moving across the stellar disk at an angle. And so you're slicing off regions both in longitude, but also in latitude. And so you have to think about the complexity of that geometry as you're thinking about the mapping. So there's a couple ways this shows up in the data because of this potential offset in scale height between the two sides of the planet that can lead to an effective seeming change in the time of transit. It can seem to delay it or have it happen a little bit earlier. And here's a plot where there's different models and they would predict different timing offsets based on what's going on with the 3D structure of the atmosphere. But it's also wavelength dependent, right? Because you may be probing through different parts of the atmosphere in and out of opacity sources. And you can also think about it. Another way to think about this is that the side of the planet that's leading as you go into transit, if you just take the transmission spectrum of that part of the planet, it will look different than the transmission spectrum of the trailing part of the planet because of these spatial differences. So again, these words are just to say what I said before. The spatial information comes from the shape of the light curve. The extra third dimension comes from wavelength dependence. Okay, I'm almost done. So the way that we measure this has analogies and differences from eclipse mapping. In eclipse mapping, we were looking for variations in the brightness emitted by the planet. Now we're effectively looking for variations in the effective size, radius of the planet as a function of location. And the way that that would show up is very similar, actually, right? These deviations on the eclipse curve due to spatial information are similar to deviations we might measure in a transit curve where different ways of puffing up or blocking information from parts of the atmosphere will lead to different sorts of shapes, residual shapes in your light curve. In terms of techniques to pull out this information, There's also been a few efforts now where you can either do more model independent techniques where you let there be one side of the planet larger, one side of the planet smaller, and then you let that influence your shape of the light curve and you fit at different wavelengths. So you basically construct two different transmission spectra for your two different sides of the planet. Or you can do a little bit of a more mathematically nuanced and I think beautiful technique that these authors call transmission strings, where you use Fourier series to describe any shape going around the planet. And so at each wavelength, you can get a different effective radius function. And that lets you pull out transmission spectra at any polar angle around the planet. Or you can use more parameterized physics-based models where you define a way of structuring the east-west, north-south, and day-to-night atmospheric structure of the planet, shine light through it, and see how you can jiggle those values in a retrieval framework to match your data. I forgot to put a box here saying stay tuned. I don't have even any JWST results to show you yet, but I have seen a couple drafts of papers that should be coming out soon with this. And again, these techniques continue to be developed. So I will end just slightly over time. And so leave up the point that we love transits and Eclipse. It's the same sort of ways that we access the information and need to think about extracting the information. And JWST finally means that we're really making 3D maps of exoplanet atmospheres. Thank you.
Hey, thank you so much for this comprehensive overview. I'm Cyril Gapp from MPIA. So you stressed how the different temperature conditions along the terminator of the planet can be revealed with 3D mapping. So I could imagine that until now, that we have neglected the 3D nature and assumed everything to be 1D, we might introduce observational biases into the results we're getting about the atmospheres. Do you think that as we now reveal the 3D nature from the data, that there might be anything we so far think we know about the planets that might not hold up?
Yeah, that's a great question. I've thought about that a little, and I'll say what I think, but then please, some observers in the audience nod at me if I've done it correctly. A lot of our transit observations are either broadband observations or over a wide enough wavelength range, and perhaps at not high enough precision for these effects to fundamentally change any of the results that have come out of transit observations so far with these techniques, with the caveat that high resolution spectroscopy may be a little bit different, and we're seeing 3D structure in interesting ways there.
Okay, that's kind of reassuring. Thank you so much.
but like, Laura, can you nod at me? Do you think that's true? Okay, good.
Hi, Emily. Thanks for the great talk.
Hi.
I just want to say Emily talked about how mapping got her into exoplanets. And as an undergrad at the University of Michigan, Emily is actually who got me into exoplanets. So again, thanks again for the great talk. And it's so good to see you here. My question is, I remember learning, and you touched on it a little bit, how mapping actually helped us verify the observation or the observational side of mapping helped us verify the theory that there is like the winds causing the eastward shift in the sunspot. And so do you expect something else, like a physical process that we can hopefully verify the existence of using the new JWST data to do the 3D mapping?
Oh yeah, so many. I mean, so the WASP-18 data, what I skipped over is that the gradient of brightness from the day side towards the terminator is so sharp that when we compare it to 3D models, we need a strong source of drag in the atmosphere, slowing down the efficiency of winds moving the hot gas. And further observations will help us get more information about really what's going on. And then also like clouds, right? You remember Peter showed this diagram where the clouds were sneaking over onto the day side, and how far clouds could extend onto the day side of a planet gives us another way to try to understand what's going on with the clouds, like how long can they exist before they're evaporated away. I just think there's so much physics. There's also, like, if you make a planet so hot and magnetized that it starts to generate its own magnetic field, then you can get flows that like wobble up and down, and then you would see latitudinal shifts, and that would tell us something was really different from what we were used to thinking about. So yeah, so much physics.